just so we can have this for later. So the solvent is present in the greatest amount. Solutes are the substances present in the lesser amounts. Right. So the substance present in the greatest amount are solvent. Substances present in the lesser amounts are solutes. And again, we can have a solution that has more than one solute. Like our sweet tea example, we have the sugar, but we also have whatever has dissolved from the tea, those polyphenol compounds and all the good colors that we get from the tea. When we think about making solutions, I want to start thinking about, what is happening at the chemical level. We see our sugar and we watch it dissolve, right? Well, what's happening to it once that sugar dissolves all the way down so that there's individual molecules of sugar floating around in the tea? And to think about that, we're going to think a little bit about electrolytes. And so we have sort of three classes of electrolytes: strong, weak, and non-electrolytes. And so let's start with a strong electrolyte. Where have you heard the term electrolytes, maybe?
Gatorade.
Yeah, Gatorade's always what I think of too. So Gatorade always talks about electrolytes, life water with electrolytes and things like this. And so electrolytes, strong electrolytes especially, are any compound, any chemical species that dissociates completely in solution. Any compound that dissociates completely in solution. Now we have a new word here, dissociate. I didn't say dissolve, but I said dissociate. We're gonna circle back to that on the next slide. A non-electrolyte, we'll talk about weak in a minute. Any compound that doesn't dissociate completely in solution. Okay. And so if you had to take a guess at what a weak electrolyte was?
Partially dissociates.
Absolutely. A weak electrolyte, I'll just throw it in the middle here. A weak electrolyte partially dissociates. Okay. Now that dissociation is a process that is exclusive to ionic compounds, right? Ionic compounds are not held together by chemical bonds. They're held together by what we call electrostatic forces. I think I've used that term before, right? Those positives and those negatives like to be attracted to one another. Well, what happens is when we put it in water, those positives and negatives get interrupted by all the water molecules that are around them. And so they kind of pull apart and break apart, and they separate from one another. They dissociate from one another. In a molecular compound, we those are held together by chemical forces, by chemical bonds, rather than just by electrostatic forces. And the water in the solution is not strong enough to break up those chemical bonds that hold those two atoms together. And so they don't break apart molecules, but they do break apart ionic compounds. And so let me put that in here. So which of these three would be molecules? Strong electrolytes, weak electrolytes, or non-electrolytes?
Non.
That's right. Non-electrolytes are going to be molecules. Right? Strong and weak electrolytes are both going to be ionic compounds. Just a quick review from chapter 2. Ionic compounds made of what and what?
Metals and non-metals.
Non-metal.
Metal and a non-metal, that's right. And then molecules are made from only?
Non-metals.
Only non-metals, yeah. And so sugar, C6H12O6, is that classified as an ionic compound or as a molecular compound?
Molecular.
Molecular for sure. And so sugar is a non-electrolyte. Right? I really should have put this picture on the next slide because I want to write more. But when we see electrolyte, what do we think about? Electrolyte sounds like?
Electron.
Electricity.
Yeah, electricity. And so electrolytes conduct electricity in solution. Right? Remember, electricity is just moving charge, right? That's a physicsy thing. And so when an ionic compound like NaCl, right, if it's just NaCl in that crystal structure, well, those charges can't move. They're locked into that crystal structure. And so they can't really conduct electricity very well. And so a lot of ionic compounds are actually very good insulators because they're locked into that crystal structure. They don't transfer that charge, even though the sodium and the chlorine both have a charge, that charge can't move very well. But when we put them in water, so we're going to start writing these subscripts on our equations, right? Sodium chloride solid goes to sodium chloride. AQ stands for aqueous. Aqueous sounds a little bit like aqua, right? And so that just means dissolved in water. Okay. And so sodium chloride, when we dissolve it in water, do we really have NaCl anymore? Are they still locked together since it's an ionic compound? No, right? What we really have, and you can think about it this way, but we don't really write it this way. We can think about this as being Na plus Cl minus. Okay? And we'll get back to that tomorrow during lecture about sort of what we do with that knowledge. But we have, for every mole of sodium chloride that we put into solution, we have a mole of sodium atoms and a mole of chlorine atoms. I should say ions, sodium ions and chloride ions. If I put sugar, since that's my favorite molecule that's not water, H12O6, that's a solid before I put it in my tea. And so when I dissolve it, it's C6H12O6AQ. Well, what happens to that C6H12O6, right? It's a molecular compound. It just stays that way, right? And so this doesn't dissociate. So it doesn't conduct electricity. sodium chloride does conduct electricity because it breaks apart in solution. It's what we call a strong electrolyte. If I go back a slide to those images of light bulbs, the two wires for the light bulbs, right, they're in this water solution. And so in the solution on the left that I just drew on, do you think that's a strong electrolyte, weak electrolyte, or non-electrolyte?
Non.
Yeah, it's a non-electrolyte. Because it's not conducting any electricity, we don't see any light in our light bulb. If we switch all the way to the other side, right, in this one, we've got lots of light coming from our light bulb. And so this guy's a strong electrolyte. And then in the middle, we have this weak electrolyte. Okay? We will talk a little bit more tomorrow in lecture about sort of the benefit, the uses of a weak electrolyte and what makes an electrolyte weak versus strong. We'll talk about that a little bit, but that is really a subject for an upper level course, but we'll touch on it, you know, why it is that way and how we can identify a weak versus a strong electrolyte. Okay. Any questions on that kind of stuff before we move on?
I have a quick question.
Yeah.
Is the electrolyte the product or the reactant?
That's a good question. So that compound we say is an electrolyte. So sodium chloride, even when it's a solid sitting in your salt shaker, we say that it's a good electrolyte because what we mean is it conducts electricity and it dissociates when it's in solution, right? And so it by itself is an electrolyte even in its solid, dry form, because when we put it in solution, it'll dissociate and it'll conduct electricity. Does that make sense?
Yes, thank you.
Sure. Anything else before we move on? Okay. So, moving into sort of how we deal with solutions and doing a little solution stoichiometry. Well, first we have to talk about concentration and what we mean when we talk about the concentration of a solution. When we say concentration, that's our way of discussing how much solute is dissolved in a solution. What is our what's our unit for when we ask how much? We kind of have two, but what's a unit for how much?
Grams.
We could use grams, absolutely, and lots of times we do use grams, but
Moles.
especially if we're going to go back and forth from one compound to another, there's a better unit.
Moles.
Moles, yeah. And so when we talk about concentration, we are usually going to talk about the moles of solute. What's our unit for volume?
Liters.
Liters.
Yeah, liters of solution, right? Moles of solute for liters of solution. We call this molarity. And it gets the symbol capital M. So whenever you see big M, think moles per liter. Michael, since you mentioned grams, one of the units that's used a lot, especially in like environmental chemistry or food chemistry or something like that, is parts per million. and we may see that this semester, so it's good to show you. Just abbreviated ppm, and that's milligrams of solute per liter of solution. Okay. Since a liter weighs a kilogram, 1/1,000,000th of a kilogram is a milligram, and so 1 milligram in a liter is 1 part per million. So that is a concentration unit that uses mass, but it's hard to go back and forth from one compound to another when we're doing masses. So we're going to stick most of the time to molarity. And so in the end of chapter 3, what the quest is on today, we talked about how many grams of something we had, and then we converted that to moles, and then did our mole to mole ratio, and then worked out how many grams of a product we would make. Right? Instead, now we have a volume, and we use concentration to get to moles. So let's do a couple of examples here. First one: how many grams of potassium dichromate are required to make a 250 milliliter solution whose concentration is 2.16 molar? We're going to set up our equation. Again, remember molarity, our concentration is equal to moles per liter. We know the concentration, 2.16 molar. When we use it as an adjective, we say molar. Not like a tooth, right? Instead of saying, that's just the adjective form of it. And so 2.16 molar potassium dichromate solution is how many moles per how many liters? Well, it tells us that it's 250 milliliters. How many liters is that?
0.25.
Yeah, 0.25 liters. So we need to figure out the moles. Once we know moles, we can go to grams. So I'm going to multiply both sides by 0.25. And I get 0.54 moles is how much I need.
Wait, how'd you get that number?
So if I multiply both sides by 0.250 liters,
Oh, okay, okay.
and since it's moles per liter, if I multiply by liters, I get moles. And this is of K2Cr2O7. And then the only thing we need is the molar mass, K2Cr2O7. Potassium 39.1 times 2 plus chromium's 52 times 2 plus 7 oxygens, 7 times 16. I got 294.2 grams K2Cr2O7. Our moles cancel, and we're left with multiplying 294.2 times 0.50, and we get 158.9 grams. Looks like we should have, this is just 2 sig figs, so 160 grams of our potassium dichromate. Okay. I did this in 2 separate steps, right? Setting it up like a molarity and then solving for the grams. You could do this all in a string. Let me do that. Just set it up for you real quick. Down here at the bottom. So we start with the one that's not a conversion factor, right? Think back to chapter 2. We start with the one that's not a conversion factor. Molarity does give us a conversion between moles and liters, and so we're actually going to start with the 250 milliliters. I'm going to go ahead and convert it to liters, but that could be one of your conversion factor steps. 2.16 moles K2CO2O7 per 1 liter times 294.2 grams K2CO2O7 per 1 mole. So that's how you would write it out as a single string for dimensional analysis, conversion factor kind of thing. Okay.
Why do we round it up so high?
So we only had 2 sig figs in our volume, 250. And so we're going to leave it 2 sig figs in our answer. All right, one more example here. The chemist needs 3.81 grams of glucose, needs to add 3.81 grams of glucose to a reaction, but she's going to add it from a solution rather than using solid glucose. Calculate the volume in milliliters if a 2.53 molar glucose solution is what she has available. So glucose, remember that's our sugar, C6H12O6. It's 180.2 grams per mole. Again, let's start with the one that's not a conversion factor, right? This converts from moles to liters. So we're going to start with a 3.81 grams of C6H12O6. Now we need to convert that to moles so we can use our molarity. 1 mole of glucose is 180.2 grams of glucose. And then it tells us that for every, what do we need to put here? We need moles of glucose on the bottom. So it cancels, but what am I converting to?
You're going to convert to liters using your molarity.
That's right. We're going to convert to liters of solution. So where does my 2.53 go? On the top or on the bottom?
Bottom.
Yep. 2.53 moles for every 1 liter. Now it asks for it in milliliters, so we got to take one extra step. There's 1,000 milliliters in a liter, right? So grams cancel, moles cancel, liters cancel, and we're left with milliliters. So 3.81 divided by 180.2 divided by 2.53 times 1,000. Who got a good answer?
8.36.
Oh, sorry, not grams, milliliters. That's right. 8.36 milliliters of that solution is what we need. Okay. We'll get a little bit more into the, using it to go from reactants to products as we work our way through chapter 4. But one more thing that I want to talk about before you do the lab experiment this evening, is dilution, right? Dilution is when we change the volume of a particular solution without adding or removing any of the solute, right? So we're changing the volume, but keeping the number of moles the same. And so in this dilution process, right, the moles before equal the moles after, right? And so if we, counted up those red spheres in those beakers, we'd see that there's the same number before and after, right? I think there's 18 little spheres in each. And so, yeah, if we have the same number of moles of something before and after, then there has to be some relationship between these two. We've talked already about how molarity times volume gives us moles, right? Because this is moles per liter times liters, and of course liters cancel. So if the number of moles stays the same, then the molarity of beaker 1 times the volume in beaker 1 has to equal the molarity in beaker 2 times the volume in beaker 2. And so this dilution equation, we just, we say M1V1 equals M2V2, and that's how we treat dilution. I lost my mouse here, but I think we're okay. Right. So let's do a quick example with this, and then we'll start the quest. So how would you prepare 5 times 10 to the 2 milliliters of a 1.75 molar sulfuric acid solution, starting with an 8.61 molar stock solution of sulfuric acid? So because we are lowering the concentration, that's what shows us, that's what tells us this should be a dilution calculation, right? That's how we know, okay, our solution's changing, our solution is changing concentration. This is probably a dilution problem, right? We're not changing compounds, it stays H2SO4. All we're doing is changing concentration, so that's our dilution. So we need M1 V1 equals M2 V2. And so let's take our first molarity as this 1.75 molar times 500, 5.0 times 10 to the 2 milliliters equals M2, 8.61 molar times, well, that's what it's asking us for. How much of that second solution do we need? Okay. So we're just going to divide both sides by 8.61 molar. Because we have volume on both sides, we don't have to necessarily convert to liters to do this math. You just need to remember that whatever your initial volume is, that's what your final volume is going to be in terms of the units.
Would you get something like 101.6?
That sounds good to me. Right, again, it's milliliters because the volume unit we started with was milliliters, right? If you convert that to liters, then your answer is going to be in liters. Okay. Okay. And so I'm going to go one step further because it says, how would you prepare we're going to take 101.6 milliliters of our acid, and what are we going to do with it?
Dissolve when I put the water into it.
Yeah, so we need some water, right? How much water would we need?
Not the same amount, right? Would it be? What would it be?
That's my question.
Man,
If I'm trying to make that much,
You need to subtract the amount of the V2 from that amount you're trying to prepare to figure out how much is going to be water.
that's right. Yeah, so 500 minus 101 gives us 398.4 milliliters of our water. Okay.
Wait, where did you get that number from?
Say again?
Where did the 39 or 398.4 come from?
Yeah, so it told us that we wanted to make 500 milliliters. Right? So 500 milliliters of our solution minus, well, we said we had 101.6 milliliters of our acid. Right? So that must mean we need 398.4 milliliters of water. Yeah, and really these should all be to 3 sig figs. So, 102 plus 398. Let's not forget our units. A bit of lab safety for you. Which do we add to which? Do we add water to acid or acid to water?
Add the acid to the water.
That's right. That's right. Okay. All right. Well, that's where I'm going to leave it for today. Okay. We will pick up more of chapter 4 tomorrow in lecture, and we will talk about precipitation reactions and solubility and all that good stuff as we continue. Okay. All right. Are there any last minute questions before we
before
we start
on the limiting reactants answers,